Hello everyone, today we are going to perform structural analysis on cantilever beam, that to a propped cantilever beam. A point load is acting at a midpoint of beam whose total length is 2 meters and the cross section is 0.25 by 0.25 meters square, and these are the material properties. So now in for structural analysis I'm going to take static structural engineering data, delete this default material. I'm going to add a new material naming it as XYZ material, adding a plasticity to it with a Young's modulus of 2 into 10 to the power of 11, Poisson's ratio 0.3. 2 level, Poisson's ratio 0.3. So now I'm going to add plasticity to this material because we are going to perform nonlinear analysis on this. And here 0. So now a bilinear isotropic hardening, this stress strain curve. So to account for plasticity in our structural analysis, we have chosen bilinear isotropic hardening. Okay, now I'm going to create a geometry in design modeler. So here I'm not going to create a cantilever beam in a 3D model because our cantilever beam is 2 meters long and 0.25 width and 0.25 meters height. So it is a very long cantilever beam. If we performed structural analysis on this cantilever beam using these dimensions and creating a 3D model, that would be a expensive, really expensive computational resources we're going to use it, and it is an inefficient way to do a structural analysis of this length. So what I'm going to do, I'm going to create a line element. A line element, if anyone of us had done structural analysis in mechanical APDL, ANSYS mechanical APDL, we would know what is a line element. A line element which is used to represent beams, trusses, also bars. So I'm going to create a line element here. A line. Now adding dimensions. It's a 2 meters. 2 meter. Coming to modeling tab. Click on generate. Our line is created. So now okay, it's a 2 meters. It's a 2 meter line. Now our load is acting exactly at the midpoint. So I have to create a point, a node here. So to apply a point load. So what I'm going to do is I'm going to split this edge. Splitting this edge, apply, and 0.5 equal halves. So 1 meter and 1 meter. Generate. Now if you see, so here is our that midpoint of this beam. So far I have only created a line, but not I have not assigned a cross section to it. So go to cross section, create a rectangular cross section of 0.25 meters, 0.25 meters. So now here a line body. Now assign a cross section, rectangular one. So now with this, we have created a line element which has a length of 2 meters and a cross section of 0.25 meters square. Now if you want to look at 3D view, create sorry. So this is that particular beam. So instead of drawing 3D model of this particular beam, I have used line element because it is the easiest and the simplest way to solve a nonlinear analysis of this long cantilever beam, so that we can reduce the computational resources and reduce the time for solving it. So now I'm going to exit, going to model, edit. So now this is our line element, line body. Here assign a material. I'm assigning XYZ material. You see, these are the details, non-linear behavior, true. So now we can perform non-linear analysis to this particular cantilever beam. Cross section, rectangular cross section. So now mesh, I'm going to create mesh, select edge filter, select, apply, add number of divisions. I'm applying 490. Now click on generate mesh. Show the total mesh is 980. So now here our mesh, you see mesh. Now if you want to see a 3D view of this particular line element, so this is our beam. So now it is a propped cantilever beam. So one end is fixed end, the other one is a hinged support. So fixed end, apply a node. So this end is fixed. Now remove displacement. Now hinged support, it is not allowed to translate, but it is allowed to rotate. So here translation is fixed, rotations are free, free to move. Now we have to apply a load. At a midpoint. Select components in the y direction. I'm selecting tabular. Now coming here at an analysis setting. So now